Hi everyone, my name is Caleb, and this summer I had the opportunity to work with Iwei and John at the Robotics Institute at Carnegie Mellon University. Our work this summer is called Causality-Based Estimation of Traffic Interaction Dynamics. The state adaptive merging algorithm presented by Iwei in her previous papers allows autonomous vehicles to safely and efficiently merge with other vehicles. However, it has two heavy assumptions. The first is that pairwise interaction between vehicles are previously known. The second is that the underlying dynamics are noise-free. This algorithm would be able to work really well in the scenario seen here, where we know the surrounding vehicles' safety behavior, and there is only one of them on the road. However, in a more realistic scenario, there will be many cars on the road, so we need to determine the pairwise vehicle dynamics of each one. Basically, what this means is that we need to figure out which vehicles are interacting with each other so that we can learn their causal behavior. For example, is K2 interacting with K1 or K3? Next is that a lot of the times in real world scenarios, the data is noisy. And like this image here, it is very hard to tell which measurements are correct and which are not. So we need to learn the safety behavior of the other vehicles regardless. All these vehicles deploy what we call a parametric-control barrier function. And at a very high level, it has a provable safety guarantee, which is derived from a forward invariant set. What that means is that states of the vehicle inside this safe set will remain inside the safe set. How exactly it does so is determined by the parameter vector called alpha, which determines the safety behavior of the vehicle, and it is used in the CDF constraint for a quadratic program formulation seen here. The Map Smoothness algorithm presented by Ma et al. Essentially tries to answer the question, how much does the variable x causally influence y, if it does at all? It does this by analyzing the mapping between reconstructed attractors of time-delayed embeddings of observed data. In other words, it tries to map an attractor formed by the y variable to an attractor formed by the x variable of its mutual neighbors. Essentially, the main idea is that it takes a neural network to map my to mx, and since a neural network can represent any smooth function, it tries to use the error of the neural network to determine the smoothness. If there is less error determined by the neural network, it will indicate a stronger causal relationship between the x variable onto the y variable. How does this apply to the autonomous vehicle case? Well, essentially, we are seeking to understand how does the CDF or H variable influence the acceleration, which is the control input. We need to do this for every single vehicle, so we treat each surrounding vehicle as a prediction vehicle. And it is tested against each other so that the interactions between K1, K2, and K3 are all known. In a simple example, we present an adaptive cruise control where the vehicle speeds up to match its desired velocity, but then it slows down and maintains its distance around t equals to 10 seconds. We see here that the CBF value, or h, dramatically drops to 0. And at this point, it influences the control input to have a sudden drop as well. This causal behavior is actually seen in the CMS algorithm where we plot the R value over time. And this is indicated by a huge spike. Finally, we learned the safety behavior of other surrounding vehicles through robust parameter estimation. This is a combination of modified least squares and a novel heuristic check. Basically, the heuristic check is that if the predicted alpha value is correct, then the CBF constraint should be active and therefore close to 0. By adding candidate values of alpha into a data set and clustering these values, we can actually derive the true safety behavior pretty precisely. Here are 30 trials under different types of noise, and we see that the accuracies are very high. And an important observation is that for specifically the uniform noise, that if we remove the top three most inaccurate predictions, the average error actually decreases by 3 magnitudes. And with that, we've lowered the 2 assumptions. I would like to thank Yue, John, Rachel, the National Science Foundation, and the Robotics Institute Summer Scholars Cohort for this amazing summer. Thank you.